All right, one more video, then I'm done with this section. Try to squeeze this in tonight. The big takeaway from the last video was this fundamental theorem of calculus. What it did is it tied together what we learned 2 videos ago, this idea of antiderivatives, with what we were talking about in the previous section, evaluating definite integrals. The fundamental theorem of calculus tells us that if we want to evaluate a definite integral, all we have to do is consider the antiderivative at the 2 endpoints of the definite integral and find the difference between those 2 values. That's kind of a mouthful, but if you're comfortable with all the notation we're using, hopefully this has a lot of meaning to you. In the last video, we showed how we can use that to much more easily calculate the area underneath a curve. But maybe you're like, yeah, but I've lived my whole life and I've never needed to figure out the area underneath the curve. Why is that such a big deal? I mean, admittedly, using the fundamental theorem of calculus is a lot easier than doing it the way you showed me in that bonus video. But who cares? What's the big deal about these definite integrals anyways? Well, in this video, I'm going to kind of start to scratch the surface to show you some of the things that you can do with definite integrals. Loosely speaking, integrals are a way to add things up, which maybe makes sense because you're sort of thinking about adding up the area underneath this curve as you go. More specifically, really what they do is if you have a function that represents the rate of change of some quantity, then the definite integral tells you how much the quantity accumulates over a given time. What am I talking about? Okay, suppose we're filling up a pool, right? So you got like a hose or something and you're using it to fill up a pool. And you happen to know how much water is coming out of that hose. You know the rate at which you're filling up the pool. It's given by this function right here, r of t, where maybe t is measured in hours. I don't know. I know this is nowhere even near realistic. I didn't work these numbers out at all, but don't worry about that. If you know the rate at which water is coming out of the hose, and it's worth pointing out that that rate is changing, right? As t changes, as time goes by, the rate changes. Anyways, you have this function that represents the rate of change of water in the pool, and you want to know how much water is in the pool after 3 hours. Turns out you can figure that out by just evaluating the definite integral from 0 to 3 of 2 over t plus 1 dt. And this would be incredibly difficult to evaluate as a limit of sums to try to do the infinitely small rectangle idea. But fortunately, if we can figure out the antiderivative, we can use the fundamental theorem of calculus and it's much easier. How do we figure out the antiderivative of this? Well, it's not obvious at all. You could think about this as 2 times 1 over t plus 1. And maybe that helps a little bit if you rewrite this way, because then maybe you see this 2 as a coefficient and you pull it out in front of the integral. And we say, okay, really all I have to figure out the antiderivative of is 1 over t plus 1. Unfortunately, we don't have a formula for figuring out the antiderivative of 1 over t plus 1. So maybe you just kind of play with it a little bit. You'd be like, well, let's see. If it was the natural log of t, then I'd get 1 over t. But I don't want 1 over t, so maybe it should be the natural log of t plus 1. Is that going to screw anything up? Is that going to work? Well, let's see. Try taking the derivative of this. If you were taking the derivative of 2 times the natural log of t plus 1 plus c, and I guess since my variable is a t here, this should be d over dt. What you would do is you'd first pull the 2 out in front, and then you would take the derivative of the natural log of t plus 1, which would kind of involve the chain rule. For the natural log part, you do 1 over t plus 1, but then you wouldn't be done. You'd have to multiply that by the derivative of t plus 1. This is all to figure out the derivative of the first term. You'd also have to figure out the derivative of the second term. But good news there, the second term is just a constant, so its derivative is 0. And more good news, the derivative of t plus 1, this is a sum. So take the derivative of each term individually. The derivative of t is just 1. The derivative of 1 is just 0. So I get 2 times 1 over t plus 1 times 1 plus 0. But 1 plus 0 is just 1. So 2 times 1 over t plus 1 times 1 is just 2 over t plus 1, which is exactly what we were hoping it would be. At this point in the class, we don't have a great way to figure out the antiderivative of 1 over t plus 1, but maybe you could kind of guess and check your way into figuring out that it's the natural log of t plus 1. And if you made that guess, you could certainly check it by figuring out a derivative. And if you don't like that at all, which I imagine you probably don't, good news, later on in the class, we're going to learn a method for undoing the chain rule. We're going to learn a method of going from here to here. But for now, maybe you can just kind of see that, yeah, that's the antiderivative. That looks like it works. But wait, we weren't just trying to figure out the antiderivative of 1 over t plus 1. This is supposed to be a definite integral. We're supposed to evaluate it from 0 to 3. What that means is, A, I don't have to write this plus c if I don't want. And B, I got to put this vertical line here and evaluate this thing from 0 to 3. To evaluate it from 0 to 3, I first plug in the 3, and I get 2 times the natural log of 4. And then I plug in the 0, and I get 2 times the natural log of 1. The natural log of 1 is just equal to 0 because the natural log of 1 is asking you the question, what power do you got to raise e up to make it equal to 1? And e to the 0 power is 1. So this is 2 times the natural log of 4 minus 2 times 0. In other words, minus 0. My answer is 2 times the natural log of 4, whatever number that's equal to. I'm not so worried about the number. I just want to make the point that an application like this, like we're trying to figure out how much water's in the pool after 3 hours, is the kind of thing that you can figure out with definite integrals. And now that we have this great method, the fundamental theorem of calculus, to evaluate definite integrals, it's cool that definite integrals can answer questions like this. Couple little points here. First of all, the question asked how much water is in the pool after 3 hours. Really, what the definite integral tells us is how much water accumulated over a given time, over those 3 hours. So really what this tells us is that we added whatever 2 times the natural log of 4 is, gallons to the pool in those 3 hours. It doesn't tell us how much water is in the pool. It tells us how much we added to the pool. The good thing is that in this specific example, the pool was empty at the start, so the amount that we add ends up being the amount that's in the pool. But you got to be a little bit careful. That's what I'm getting at here. Implied in this problem, because we got an empty pool, is that we kind of start out at 0, but that won't always be the case. To show you an example where that's not the case, let's look at this problem. Suppose the mold on a piece of bread is growing at a rate of g of t equals e to the 2t power. If you start out with 1 milligram of mold, how much mold is on your bread 2 hours later? And we'll assume that t is measured in hours up here. Well, we can figure out how much mold accumulates in that 2 hours by evaluating the definite integral from 0 to 2 of this function g of t, e to the 2t power. And then after we figure that out, maybe we can use that to answer the question. To figure that out, we want to use the fundamental theorem of calculus. To use the fundamental theorem of calculus, we need to figure out the antiderivative of e to the 2t power. Again, we don't have a method of figuring out this antiderivative just yet. So maybe you'd have to guess and check your way in there. You'd be like, well, I know the derivative of e to the t is e to the t, so maybe I should try doing e to the 2t. Maybe that's the antiderivative of e to the 2t. Does that work out? No, it doesn't. Because look, if you're taking the derivative of e to the 2t, you'd have to use the chain rule, right? You'd first take care of the outer function, the e to the stuff, but then you wouldn't be done. You'd have to multiply that by the derivative of that stuff. The derivative of e to the 2t is 2 times e to the 2t. But we don't want the derivative to be 2 times e to the 2t. We want the derivative to just be e to the 2t. So this is not the antiderivative, because the derivative of this produces an extra 2 up here. So what can we do to this so that we won't produce that extra 2 up there? Well, it's easy. Just toss a 1/2 down here. The derivative of 1/2 e to the 2t, what you would do is you'd pull the 1/2 out in front, completely leave that alone, and then you take the derivative of e to the 2t, which, as we showed a minute ago, was 2e to the 2t. The 1/2 and the 2 would cancel out, and we get e to the 2t as our answer, because the derivative of 1/2 e to the 2t is equal to e to the 2t. The antiderivative of e to the 2t is 1/2 e to the 2t. Technically, the antiderivative also contains a plus c, but I don't have to write that plus c because I'm going to evaluate this thing from 0 to 2. When I plug in 2's, I get 1/2 e to the 4th power. When I plug in 0's, I get 1/2 e to the 0 power. E to the 0 power is equal to 1, so my answer is 1/2 e to the 4th minus 1/2. Or if you want, you could factor out that 1/2 and rewrite it as e to the 4th minus 1. Or if you're really feeling like flexing algebraic muscle, maybe you call it e to the 4th minus 1 over 2. Whatever. This is the same as this, same as this. I don't care what you use. You're like, great, so any one of these is my answer? No. Any one of these tells you how much mold accumulated in those 2 hours. But the question is, how much mold is on the bread in 2 hours? We started out with 1 milligram of mold. We started out with 1 and we accumulated this much more. So the answer to how much mold is on the bread 2 hours later is this 1 plus this answer, 1/2 e to the 4th minus 1/2. I can simplify this a little if I want. The 1 and the negative 1/2 make a positive 1/2, and I can call it 1/2 e to the 4th plus 1/2, or some other form that looks like one of these guys. The point that I wanted to make is you got to be a little bit careful. This tells you the accumulation, not the amount of mold on the bread. And people often confuse those two ideas. One more example, one more application of this, and then we'll be done with this section. A very common application of integrals deals with velocity and distance. If you have a function that tells you velocity, the antiderivative, the integral, is going to tell you the distance. And yeah, maybe that makes sense to you because we've already been thinking about the derivative of the position gives you the velocity. So it makes sense that the antiderivative of the velocity gives you back the position. A quick comment here, I had to specify that we have a positive velocity function because really this doesn't give you the position, it gives you the displacement. It tells you the change in position. If we're always heading in the same direction, the distance you travel is the exact same as the displacement, the difference between where you end up and where you start. But when you have velocity functions that are both positive and negative, displacement is different from distance, as I'm going to show you down here. This function that you've seen before, we're going to assume represents velocity. It's going to represent the speed of a ball that you throw straight up in the air. So when the velocity is positive, the ball is going up. And when the velocity is negative, the ball is coming down. It's tempting to look at this picture and be like, oh yeah, this is the highest the ball ever gets. And then it's coming down and it crashes right here. No, this is not the position. This is the velocity. The position is not pictured. It's not graphed. I can graph it for you though. We're going to start with this ball at a height of 1 foot. Here's 1 foot right here. And this ball is going to go up. How fast is it going to go up? Really quick. The slope of the tangent line to this curve that I'm drawing in purple should be 3, the height of the velocity function, because the velocity is the derivative of the position function. So what I want to do is I want to draw something that's going up really, really quick, but it starts to go up slower and slower and slower. And there's some point over here where this ball reaches its maximum height. The velocity is 0. It's no longer going up. It kind of pauses for a split second and it starts coming back down towards Earth. After 4 seconds, the ball is right here. What I'm trying to figure out is how high is this ball? The x coordinate of the graph in purple is 4. What I want to know is what is the y coordinate of the graph in purple? That's really hard to figure out because we don't know the equation of the graph in purple. But good news, we can figure it out. The ball starts out at a height of 1 foot, and since we know the velocity function, we can use the definite integral to figure out the displacement of the ball. The definite integral from 0 to 4 of 3 minus 1/4 t squared will tell us how much the ball is displaced between 0 and 4. In other words, how much higher up it is 4 seconds after we throw it than it is 0 seconds after we throw it, at the instant that we throw it. Good news, it's now really easy to evaluate this definite integral. We've done it several times. Take the antiderivative, which is 3t minus 1/12 t cubed, and evaluate that thing from 0 to 4. When we evaluate it at 4, we get 12 minus 64 over 12. When we evaluate it at 0, we get 0. If you want, you can write something like this to really show your work. And as we've seen several times, 12 minus 64 over 12 is the same as 12 minus 16 over 3, which is 36 over 3 minus 16 over 3, which is 20 divided by 3. So the height of the ball is 20 over 3? No. The displacement of the ball over this time period is 20 over 3. The ball started out at a height of 1, and its height has increased. In other words, the distance from here to here, which isn't the high point of the ball, it's the height of the ball after 4 seconds, which is a little lower than the high point because our velocity is negative after this point. The displacement is 20 over 3. So what's the height of the ball? Well, it started out at 1, and it's gone up a net amount of 20 over 3? The answer to the question is just 1 plus 20 thirds. In other words, 23 thirds. Feet, I guess, is the unit that I'm using here. Although I don't care at all about units, I just care about that answer, and I care about calling this section done.